Okay, let's go and get started today. Today we're going to be having class 1, lecture 1 of ETEC3702 concurrency. So welcome, and let's take a look at what we're going to do today. So what we're going to do today is we're going to start off with looking at the syllabus and kind of explaining your course expectations. I'm also going to mention my teaching philosophy. We're going to look at the course goals. In other words, what are we going to do this semester? What are the goals? Why are we doing it? And then we're going to dig into a little bit of what is concurrency, and then we're going to look at why are we studying it. Why is there a class in that you're taking right now? All right, so let's go and get started. So let's start off with looking at the syllabus, and let me explain the course expectations a little bit here. So give me a second here while I switch over to the syllabus. Okay, there we go. All right, so to start with, like I said, this is 3702, ETEC3702. There are two sections. There's the 2 to 4:15 section on Tuesday, Thursday, and then on the same day, there's the 5 to 7:15 section. So what I would suggest, since we're doing the lectures via video, I would suggest during that time span, you reserve time to watch the lectures, do any of the labs, work on the labs at least, look at the course site to see if you missed any handouts or any quizzes or any labs. But don't just say, well, it's lecture video, so I'll just watch them later in the week, or I'll watch them, I'll binge watch them all before the midterm. I would not suggest doing that. And based on my experience over the last couple semesters, students who have tried to do that or try to get by without going through the videos have been unsuccessful in those classes. So it's your responsibility to make sure you're watching the videos, you're keeping up with the stuff on the course site, you're doing the work, you're asking questions if you have them. If you're struggling, let me know, but you need to have discipline. And one of the ways to do that is to treat it like a normal class. Say it's 2 o'clock. I'm going to sit down and I'm going to log into the course site and I'm going to look at the stuff that's on there. I'm going to watch the lecture. And then I'm going to perform the lab or take the quiz that goes along with that. So make sure you do that. We may have some sessions where we meet in person, but predominantly all of the lecture videos are going to be distributed online via video format. If you're watching this, it'll be similar to that. And the other part of that is the exams, however, will be held in person in the classroom. So 327 ATC is where you should go for that. All right, instructor information. A lot of you know me. Some of you may not. My name is Paul Yost. If you need to refer to me or talk to me, Paul is fine. We don't have to keep things super formal. So just say, hey, Paul, I was having trouble with assignment, whatever. Just use my first name. My office is in 307 ATC building. You all know where the ATC building is at this point in your academic career, and you probably know where my office is. But I'm on the 3rd floor. Walk around the back. My office is back around there. So if you need to schedule a meeting or come in and see me, that's where we can meet. All right, my office hours are Monday, Wednesday, 1:30 to 2:30, and 4:45 to 5, and then Tuesday, Thursday from 4:15 to 5. So I'll be available for office hours by phone or Zoom conference. Due to the pandemic, I won't be just in my office a lot waiting for people to come in and talk to me. But if you text or call or send me an email, we can certainly arrange a Zoom meeting or a face-to-face meeting if you need that, or if you think that would be helpful. Just get a hold of me and let me know. My phone number that's listed there is my mobile number. So if you send me a text message or you give me a call on that, I'll be happy to talk with you. If you do call and I don't answer, it's either because I'm on the phone with somebody else or I don't know your number. So leave me a voicemail if you don't get a hold of me, and I'll call you back. And you could also send me a text message and say, hey, this is Susan from your concurrency class. I have a question. And then I'll send you a message back saying, okay, well, give me a call. I'm available now, or I might just call you back. Or we might text each other back and forth and set up an appointment on Zoom or something like that. Now, one special note about my office hours during the pandemic is I'm going to be conducting them remotely, which means that I'll be fully available via a number of means. You can get a hold of me on email or text message or mobile phone, Facebook Messenger. I would shy away from using Discord because I don't have that active on my laptop. I find it too distracting while I'm doing other things. So any of those other things are fine. But you can send me a message on Discord, but it might be a day or two before I actually get around to logging in and checking it. Also, I'm available for face-to-face meetings if you need to have a meeting like that. Just contact me. We'll set up an appointment. I'm more than happy to come in. I only live, and my business is only a couple blocks away from the university, so I'm happy to come down there anytime, including evenings or weekends if necessary. Just contact me and we'll set something up. If you do set up something to come in and meet face-to-face, bring a face mask. Make sure to use the hand sanitizer on your hands after you walk into the office complex up there. There's a bottle of hand sanitizer there or one right outside the elevator. Just do that before you come into my office. All right, there aren't any textbooks for the class. All of the information will be provided via the lecture videos, lecture slides, supplemental material, code examples, and things like that in the class. So I'll provide links to things periodically. Again, it's your responsibility for getting all that stuff. All right, the course description. And this is the catalog description. It says, this course examines principles of concurrent and parallel programming. These may include synchronization primitives such as semaphores, conditions, and barriers, techniques of mutual exclusion, parallel algorithms. There's actually a missing O there. Algorithms, synchronous and asynchronous message passing, remote procedure calls, task rendezvous, callback-based parallelism, and popular process interaction paradigms. Now, a lot of that isn't going to make a lot of sense right now until we know what concurrency is and know why we need it. But note that we are going to cover a lot of those things in this class. Attendance, I don't take attendance. It doesn't make any sense, especially for a lecture, video-based lecture class. And really, even if we were meeting face-to-face, I still probably won't take attendance. It's up to you to be responsible for the material and be responsible for your own learning. This is for your benefit, not for me to be mean to you. So if you don't want to watch the videos and do the work, then don't. But you're not going to get a good grade if you don't know the material or learn the material and do the work that's in the class. All right, speaking of that, the grading system is the majority, 40%, is the homework and programs and quizzes that you'll have in here. 25% is the midterm exam. 35% is the final exam. Now, there is one other rule on the final that I need to mention, and that is you have to pass the final to pass the class. If you fail the final, that's kind of my way of making sure that when I give you a passing grade, that you have met a minimum level of understanding of the material. And so I've taught for a lot of years. I've taught concurrency and other related classes for quite a few years, so I know the level to put the final at to make it so that if you pass, you've learned enough. If you fail, you don't really have a mastery of the material that allows me to feel good about sending you on unprepared. So that's the grade system. Here's the grade scale. Pretty standard, but notice what is an F? Well, anything above 59.5 really would count as a passing grade. Anything below 59.5, since I do round, anything below that would be considered failing. And again, you have to pass the final to pass the class. All right, a couple important rules. Don't cheat on anything. Don't cheat on the assignment. Don't cheat on the tests. Don't cheat on the quizzes. And when I say don't cheat on those, that means if I give you an instruction like write this program, but don't use the internet and don't Google it. If I find that you did use the internet and Googled it and took somebody else's solution, or you posted it onto Stack Exchange or whatever, and had somebody else on the internet give you an answer that you then gave to me, then I will deal with those infractions severely. I think being intellectually dishonest is not a good character trait, and it shouldn't be rewarded. So being honest, having integrity is important. It matters in life. So I will treat you with honesty and integrity and respect. I expect you to treat me the same. The other thing is, and this one's not as big a deal, but no disruption. Not as big a deal for online distribution of lectures anyway. But be polite, be respectful, behave professionally. If we have a class session or an exam session, don't be disruptive to the people around you. They're paying to learn material and get an education. It's important for you to not interfere with that, with other people getting what they want to out of the class. Just like it would be unfair for you to go to a movie and have people talk on the cell phone, or I don't know, have a dance party in front of the screen. Don't do things like that when we're in class. All right, the programming assignments, it talks about those, but to turn those in, they'll be submitted on Blackboard. At this point, for a 300 level class, everybody should be familiar with Blackboard and turning things in. If your Blackboard isn't working for some reason, or you can't log in, or your password, for whatever reason, has been forgotten or lost, and an assignment's due, feel free to send me an email and ask me, hey, what do I do? I'll help you either get logged in. If we can't figure that out, then I might say, well, email it to me and I'll grade it. But don't just email me assignments and expect that I'm going to grade them or count them, because my rule is, unless you talk to me ahead of time and make alternative arrangements, if it's not on Blackboard, it's not going to get graded. So make sure to submit the stuff on there. All right, exams and quizzes. They're going to be 2 exams, a midterm and a final. We already mentioned that. And they'll be announced at least 1 week before I give them. We'll probably also have like a study guide outline and things like that that are posted before that. But I'll announce the exams at least 1 week before they're given. So no makeup midterm or makeup final unless you make arrangements with me or have a legitimate excused absence of some sort. The quizzes, I may give those at any time without announcing them, but a lot of times in the lectures, I'll say, hey, this would be a good thing to have a quiz over. I might say that before the next class session. I might say that. So I won't generally announce them. I don't have to announce them, but I might hint that they might exist. So makeup pop quizzes will only be given if you have an excused absence that's valid. And it's your responsibility to make sure that you know when the exams are, when the quiz, or to make sure that you take the quizzes during the assigned window of opportunity if they're posted on Blackboard. And make sure that you communicate with me if you have some excused absence. Like, let's say you're sick, you get diagnosed with COVID, you can't come to class, or you're in the hospital or something like that. Make sure to get a doctor's excuse if you are in that situation, and make sure to communicate with me if you can, so that I can be aware of that and not end up giving you bad grades on things that you should have an excused absence for. Now, a couple final things here. The ADA statement: if you do have a disability, work with the Office of Accessibility Services to get an accommodation letter. Even if you have an accommodation letter already, I will have gotten that. But before the exams, or if you're struggling with other things during the semester, communicate with me. Let me know. I'll work with you. I'll make sure that your accommodation needs are met, but I need you to communicate with me. Some people that have accommodation letters feel like for certain classes, it's fine. Some people feel like they need some accommodation made, but I'm not a mind reader, so I need you to talk to me about that ahead of time and do so before the exam. If that's a larger font on the test, or if that so you can see it more easily, or if it's a quiet place to take the test, or any of the other possible accommodations, just communicate with me. You have to let me know so I can help you. All right, the Title IX statement there, you can read that on your own, but basically it says that the university is committed to maintaining a learning environment that's free from a whole lot of bad things, harassment, discrimination, for any number of reasons there. And that could also be some sort of retaliation for something that you've done or said or believe, or who you are. But the idea there is any of those acts that violate somebody's fundamental rights or dignity, we're not going to tolerate those. So if you see something like that, or you're the victim of something like that, feel free and safe to let me know. Or if you don't want to let me know or don't want to talk to me about that, then talk to somebody in the Title IX office. Specifically, the contact information for Monique Harmon is on there. She's the Title IX coordinator, and her phone number's there. So if you hear somebody doing something that they shouldn't be doing, or somebody intimidating somebody or harassing them in some way you feel is inappropriate, it doesn't hurt to have a conversation with me or with Monique or any of the other faculty members. But note that if you do have that conversation and it's something that seems like a genuine infraction, that I have to report it to Monique. Now, that doesn't necessarily mean there's a formal report. It just means that the person who's the victim of that, whether that be you or somebody else, might be contacted and asked and kind of what the situation is, and it might they might need help or might be entitled to some sort of accommodation based on that. So if you see something, say something. If you're the victim of something, get help, because we don't want that kind of behavior in our environment here. Okay, so that's it for the syllabus. So I went through that relatively quickly. The main things to note for you guys in this class are going to be get the lectures and the other materials off the Blackboard course site predominantly, and communicate with me if you're having trouble or need to meet. Okay, let's go back to the presentation. So we looked at the syllabus. Quick note about my teaching philosophy, if anybody in here has not had me in a class before. My teaching philosophy is the phrase to teach does not make much sense. And the reason for that, well, you might think, why would I say that as a college professor, to say to teach is nonsensical? And the answer is that it puts the emphasis on the wrong side of the equation. That, like other things in the world, when you do something to them, they don't have a choice in it, like to punch, to kick, to throw, to drop, to I don't know, tap, whatever. But to teach, I can't just teach you things without you being the active entity that's open to learning. And so what I need you to do for this class, and probably what you should do for your other classes, is be an active participant in your education. So in other words, if you're struggling, be active and get help. The whole point of this class is for you to learn stuff, not to fulfill some requirement. And that's an important thing for you to make that kind of paradigm shift, to say, rather than, oh, I have to take concurrency, and oh, I have to take the test and I have to study. Think about it as this is a chance for you to learn stuff that can change your career trajectory, can change the way you think about the world around you, can change the way that you write code and design systems and build stuff, and it can allow you to do things that otherwise you wouldn't be able to do. So think about it as an opportunity to put more tools in your toolbox, or spells in your spell inventory, or something like that. So think about it in those terms, and then try to make the most of it while you're here. And I'll try to keep things relevant and exciting as much as possible, but that doesn't mean that it's always going to be easy. All right, so the course goals in here are going to be, we're going to have a mixture of some theoretical things, but we're also going to write code that does stuff. So we're going to have a mixture of theory, we're going to do some practice, and the idea is here to prepare you to be good developers and good engineers. And concurrency, even though maybe you haven't heard of it or maybe don't know a whole lot about it, is a really important thing to be a good developer and a good engineer, is to have a good working understanding of concurrency. And the reason for that is concurrency bugs are insidious and they're really dangerous. And we'll see some examples of that here later on today. And almost all real world systems have some sort of concurrent aspect to them, whether they have concurrency in them. And so if every piece of software and every system design has concurrency in it, and it can be really dangerous to not know how to control it or to have those bugs show up in there, really difficult to test as well, then it's important that you have a good feeling for when you need to worry about it and what concurrency actually is. The other part of this is to kind of improve your skills, improve your ability to do problem solving, analysis of problems. But I also want you to have an exposure to an understanding of concurrent systems and the kinds of problems that you might encounter, gain knowledge and understanding about those things, and then develop your programming skills, including How do you write concurrent code? How do you control it? How do you debug it? All right, so good students in this class, you're going to be interested and self-motivated. You're going to be focused on those learning opportunities rather than just getting through the class. You need to be willing to do the work. You also need to be tenacious. Some of the assignments are going to take some effort, some thought, maybe a couple of attempts. So if something isn't working the way you think it should, figure it out. If you get stuck and you need help, ask me. If you get stuck and feel like you've been spinning your wheels for a while and you don't know what to do next, talk to other people in the class, see if they know anything, or get a hold of me and I'll meet with you, or we'll have a Zoom and we'll talk about it. So your job is to make sure that you're getting everything that you want out of the class. My job is to be your guide. I like to think of it more as rather than a teacher standing in front of the classroom forcing people to do things. I want to be like your guide or your Sherpa that's leading you to the top of this mountain where there's some really cool stuff you'll learn and really powerful things that you're going to be able to do once you've gotten to the top. And so my job is to make it as easy as I can for you to learn the stuff and to help you learn how to learn and to help you think about how to think about these problems. And that seems a little bit paradoxical or self-referential, but this thing here is a really important skill for you to learn, is how do I learn how to do this? How do I figure out how to figure things out? But my job is to be your guide. Now, let's move on and actually cover some of the material for the class. So first off, concurrency. That's what the name of this class is. That's what it is. And I read you that description, the catalog description from the syllabus, but I want to spend a little bit of time today digging a little bit deeper into what concurrency actually is and why we actually study it. So the first thing here, concurrency is the study of concurrent systems. Well, that, speaking of self-referential, concurrency, studying things that are concurrent. Well, what does concurrent mean? So if we break that down into the parts of the word con, in this case not being like a con artist or con man, con here meaning like with, like chili con carne. That's like chili with meat. So with, con means meat. And current has kind of two meanings. One would be like something that flows, flowing. Or one would mean like current events, like right now. Meaning with respect to time, right now. But both of those kind of fit. So something that's with and flowing, well, if two things are flowing with each other, that makes sense. Or two things happening right now together. So to get a better feel for that, let's look at the dictionary definition. And the dictionary definition of concurrency, or concurrent anyway, notice it's an adjective. And it means existing, happening, or done at the same time. So there are 3 concurrent arts fairs around the city. Or you might think of like this person is serving 2 concurrent life sentences for the crimes that they committed. So concurrent means 2 things happening together at the same time. So why are we studying that? Well, we're going to discuss that question today. And I want to hopefully by the end of the day convince you that studying and understanding concurrency is really important for you as an engineer or developer. And not studying and not understanding concurrency, I hope to convince you that that's something that could be really dangerous to not understand anything about it. Now, a starting point for talking about concurrency and looking at it is I want to look at a sequential system. In other words, I want to look at something that's not concurrent first, and then we're going to move through to look at concurrent systems after that. All right, so our starting point is, excuse me. That doesn't mean I'm sleepy or tired. That's just when I talk on these lecture videos, I notice that I don't get enough oxygen as I'm talking. And that makes me have the yawn reflex. All right, anyway, the starting point for what we're doing here is sequential programming. That means the code order specifies the instruction order. And programming languages, the ones you're probably used to dealing with, I don't know, like C language or C++ or Java or Python or I don't know, Ruby or something like that. In those programming languages, the code order or the language itself is used to specify instructions that are in the language or commands that are in the language. and provide abstraction. It also provides kind of syntactic constructs like for loops or while loops or assignments or if statements or things like that. But at the end of the day, the code gets converted into CPU instructions that get carried out. And the language the syntax of the language and the constructs that that language kind of embodies or allows, they tempt us to think of solutions to problems in terms of the constraints that that language offers. So for example, if you have a language that doesn't have pointers, you'll probably tend to think about how to solve problems differently than if you have a language like C or C++ that have pointers in them. There's just a different way to go about solving problems based on the way the language was designed. If you have an object-oriented language like C++ or Java or even Python, you'll probably think about how to solve problems differently than if you have an imperative language like Pascal or C. So it's important to understand that a programming language, constrains how we think about solving problems. And one of those constraints is on the sequential nature of doing one thing after another. All right, so many languages are built around that kind of sequential constraint because the computer architectures are sequential, following a von Neumann architecture. And if you reminder of how the von Neumann architecture is set up, you have a CPU that carries out instructions. The way it does that, it fetches an instruction, decodes it, in other words, figures out what the instruction is, and then carries out the steps to do that. And then it repeats that. So the processor is just constantly get an instruction, figure out what it's telling me to do, carry it out, get another instruction, look at it, carry it out, get another one, look at it, carry it out. And that kind of processor cycle is just repeating over and over and over again really, really fast. Now memory is holding data that those instructions use, but it's also holding the instructions themselves. It also has the I/O, memory mapped I/O, where the data is coming in from devices. It shows up in certain places in memory. So really, we just have a CPU fetching an instruction from memory, decoding it and executing it that may include putting data into memory, pulling data out of memory, and some of those memory locations might be connected to some sort of input and output device, like the monitor or the keyboard. Now, they also, though, they carry out those instructions sequentially. In other words, it fetches one, decodes it, executes it, and then goes to memory and fetches the next one, decodes it, executes it, and then goes and gets another one. So the natural way to write a program for a von Neumann architecture machine is in a way that matches that, which would be sequential execution. All right, so let's look at a little sample sequential program here. And the sample sequential program here, and this doesn't really do anything. This is like a trivial abstraction of a program. But here's our program. It has three statements. Statement 1, Statement 2, and Statement 3. And it basically does those one, and then the next, and then the next. So for that to be sequential, notice I have a little bit of notation here that I've adopted, or that we're using here. So for a sequential program, for this to be sequential, what this upside down A followed by an E followed by that dot means, and these arrows, well, let's take a look at what that means. Essentially what that means is this upside down arrow means for all. And if you've taken discrete math or some other math class, you may have been exposed to that notation before, but that means for all. And the lowercase e in this case, we're using that to mean all valid executions. So for all executions that are valid, and the dot means it is true that, and the arrow means proceeds. So in other words, if this is sequential, it's saying for all valid executions, it's true that A precedes B, B precedes C. So in other words, A has to start and finish before B starts, and then B has to finish before C starts, but it has to be true for all valid executions that this full ordering like this is maintained. So here's a sequential program. I equal 5, j equal I plus 10, k equal j minus 2. So let's call those A, B, and C to fill in something from this abstraction we have here. Let's make something a little more realistic. And there's a little bit of code over there on the left, A and B and C. So notice here that the order is important here. In other words, we have to run A before we can run B, and we have to run B before we can run C. So we have to complete assigning 5 to I because we're using the I value here. And we have to complete the assignment of J before we can use J down here. Otherwise, we'll get weird values from this. So note that B and C up here, in other words, this line with a J and the line with a K, clearly have sub-operations inside of them. In other words, it's not just one atomic operation. There's little operations. Like, for example, let's just look at the line with J. We have to get the value from I, we have to get the number 10, and then we have to add them, and then we have to store that into J. So fetch I, load I, the value of I into the processor, get the number 10 into the processor, have the processor add those two things together to get the result, and then stick that into variable J wherever it is in memory. So we've got several substeps here. Same thing on this one. But what about I equal 5? Is that atomic or does that have substeps? And it actually turns out that has substeps too. Load the 5 into the processor, stick that 5 into the place in memory where I is being stored. So when we think about those A, B, and C having substeps, we could think about them like this. So A could have however many substeps it has, starting with 1, going up to, I don't know, M, however many there are. B would have its own set of substeps, and so would C. So notice this, but every one of those substeps has to be have this precedence or this precedes operator in it as well. So in other words, when I say for all valid executions, it's true that A precedes B precedes C. They all have to be in an order like that. But then if we expand that or substitute the substeps in for this larger kind of abstract thing A, we get all of them like this. But you'll notice that this entire thing is, even if you get this down to the smallest level possible for each of these substeps, it's totally ordered. In other words, A1 has to start and finish before A2 can run, which has to finish before A3, which has to finish before, and so on, all the way up to the last part of A, which has to finish before B runs, which has to B1 runs, that has to finish before B2, and so forth for all of the parts of B. And then the same thing for C. In other words, it's a total ordering. So a sequential program ends up being a total ordering, and therefore the execution is deterministic. Every time you run this code back here, you're going to get the same results in I and J and K because it's going to run in order. I is always going to have 5 when this is done. J is always going to have 15 when this is done. And the K is always going to have 13 when this is done. So deterministic execution results from a total ordering that results from a sequential program running. So sequential execution, to circle back and mention that one more time here. Essentially, the order of the statements specifies the execution order. That makes it deterministic. It means the execution is deterministic. You'll run that program, you'll get the same result every time you run it. Instructions are fully ordered. They always have the same ordering. And there is no overlap of instruction execution. So that's usually good, as in our previous example back here, because if we ran these in different orders, potentially different orders, and scrambled them around, we'd get different values when we run that, and it wouldn't necessarily give us what we want out of that program running. So order can matter, but sometimes it can't. So let's look at another sequential example here. And in this sequential example, we have the same kind of thing, but we've got 1, 2, 3, 4 assignments. J equal 10, K equal 20, M equal 15, N equal 1. And then we have this final assignment to I where we're doing a mathematical formula. So that will be compiled as a total ordering if we compile it sequentially. So in other words, J will get assigned the value of 10, and then K will get the value of 20, and then M will get the value of 15, and then N will get 1. And then we will perform this operation down here, which will consist of adding J and K, adding M and N, multiplying those results together, storing that into I. So that'll be compiled as a total ordering. But the question is are all of those orderings necessary to get the same answer or the right answer when we run this? And the answer is no, it's overspecified. Okay, so I'll give you a couple seconds here to think about how is that overspecified. So in other words, which of these lines or operations could we change around and it would still give us the same answer? And you might think, well, what if we just switched these two lines? We just swapped them around, put the j equal 10 after the k equal 20. We'd get the same result. We move the n equal 1 up to the top. That would work. Because you'll notice that none of these depend on each other happening first to do that. But we could not move this I equal line anywhere else other than the last thing, because then we would be using the values before they actually got assigned. So we could not move this one. So in other words, this line has to be last. All of these ones, doesn't matter what order they're in as long as they happen before that one. All right, so how can we fix that problem? Well, we can relax the constraints by allowing parts of that to happen concurrently. And in other words, allowing them to overlap each other, happen at the same time. Now that we're going to introduce a new operator here called the concurrent with operator. And so in other words, what we're doing right now, this double vertical bar, we're using that as the concurrency operator. That's not logical OR like it is in C language or C++. That's the concurrency operator with how we're using it right now. So that concurrency operator there, the way I would read this statement here is A concurrent with B. Now the concurrency operator means that those two instructions, or these two things on opposite sides of the concurrency double bar, may be executed concurrently. Now note that doesn't mean that they're obliged to overlap or they have to run at the same time, but it means they're allowed to overlap and it's okay for them to do that. So in other words, you could still have A and then B, or B and then A, or they could overlap in any number of possible ways like this. This one could be contained inside of that one could be inside of that, they could look like that or that. They can overlap in a lot of different ways. And it's still okay. So this is allowing those to overlap each other. So formally, the concurrency operator, the description of it looks like this. In other words, A concurrent with B, or A is concurrent with B if and only if, and this backwards E is there exists. So A concurrent with B if and only if there exists some valid execution such that A does not completely come before B, or A does not precede B, and B does not precede A. So if A doesn't come before B, and B doesn't come before A, there's only one possibility, and that's that they overlap somehow. So that's what we say when we mean that two things are concurrent, is that they are allowed to overlap, but not obliged to. All right, so let's go back to our example and then look at how we can use concurrency notation like this to come up with something that's less constrained than what we had before, where it was A precedes B, precedes C, precedes D, precedes, and then this whole line here. Now what I've done up here, notice I've added some comments in here to label these. So J equal 10, we're going to call that A. K equal 20 is B, M equal 15 is C, N equal 1 is D. And now notice here, I've got this divided up. So E is this addition of J and K. F is the addition of M and N, and then the multiplication of that times that is G, and then the assignment back to I is H. By allowing concurrency in this, we can get this, where A, B, C, and D can all happen at the same time or overlap each other because they don't depend on each other, but we have to finish all of those before we can use the values to do E and F. But E could happen at the same time F is happening. So there's E concurrent with F, because these don't depend on each other. They're not using any results from each other. And then we do the multiplication, and then we do the assignment into I. So here's what that looks like. For all valid executions, it's true that A or B or C or D all can overlap, but then all of those have to finish before we do E and F, but the E and F can happen together. But that has to finish before we can do the multiplication, which has to finish before we can do the assignment into I. So I'll give you a second to look at that and look at the code. And then I'm going to ask you a question here. Okay, so make sure you understand what that's saying there. And now I'm going to ask you a question. Is that still overspecified? And the answer is yes. You can tell by my little comment I put up there. It is still overspecified. So can you see how it's still overspecified? Are there things that are coming before other things that don't really need to be? All right, so let me ask it this way and see if you can come up with the answer on your own. So looking at E, what values do we need for E to complete? We really only need J and K. We don't care about M and N to compute E, but notice here for E to have a chance to run, A, B, C, and D have to have completed before we ever run E. But why do I care about what's happening with M and N to have E run? But here's M, and there's N, and C and D. I don't care about those to have E run. So this is overspecified the way it is right now. All right, so how can we fix it? How could we rewrite this thing here so that it's no longer overspecified? And I'll give you another couple seconds to take a look at that and see if you can figure out how you would do that. But we know, and I'll give you a hint, A and B have to happen before E, and C and D have to happen before F. But both of those branches could happen together with each other. All right, so here's what that looks like. So for all valid executions, it's true that A and B have to complete before we can do this, use those values to do this addition for E. And then C and D have to complete before we can do F. But both of those paths could be run concurrent with one another. But all of that has to finish before we can do the multiplication. And then the multiplication has to finish before we can do the assignment. So that version there that we have with all that stuff plugged in is no longer overspecified. But notice in our programming language, we're J equal 10, K equal 20, M equal 15, N equal 1, I equal J plus K times M plus N. That is specifying an order that's not necessary. We could actually relax that into something where they can overlap each other like this. Okay, and that brings us to this concept of what we're going to call the CSP model of concurrency, which, depending on what resource you look at, it'll be described as the concurrent sequential process model of concurrency, or it might be the communicating sequential process model of concurrency. But the idea is each process is sequential. In other words, each individual thing that's running is totally ordered, but now we're allowing those processes to overlap each other, to overlap their execution. They're not obliged to overlap, but they may overlap. They're allowed to. So also no timing assumptions are made with those. So if we have A concurrent with B, and those things are allowed, each A is sequential, B is sequential, they're allowed to overlap each other. But we're not going to make assumptions on the timing that they're both going to start at the same time and finish at the same time. It might be A starts and finishes before B does anything. It might be that B starts and finishes before A does anything. It might be A starts and then pauses for a while, and then B runs and finishes, and then A resumes and continues on. We're not making any assumptions whatsoever that they're running at the same time, finishing at the same time. So let's look at that a little more carefully here. So let's say we have two processes, A, totally sequential, B, totally sequential, but now we're going to run them together concurrently. So A concurrent B, and the two processes are allowed to overlap. So the effective orderings that we would get out of that would be, well, A could run first, or A1 could run first, and then B could run and finish, and then A2, A3, or B1 could run first, and then B2, and then A1, A2, and then B3, and then A3. Notice there's a lot of ways those things could overlap. So if we have, let's say this is A. Well, let me do this way. This is A. This is B on this side. What are all the ways that those can overlap each other? What are all effective orderings? Well, A could run completely, and then B, or B could run and then A, or they could overlap like this, or like that, 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 or like this. There's a whole bunch of ways that those can actually overlap each other and have an effective ordering that goes A1, A2, A3, B1, B2, B3. And I'm not going to ask the question right now, but coming up, probably next class, I'm going to ask the question, well, how many orderings are there? We've got 2 processes that each have 3 things. What are all the possible orderings? How many are there? Effective orderings of these 2, just those 2 really simple processes. You can see there's a lot of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'll let you figure out how many there are. Okay, so in that CSP model of communication, we already said, well, let's just say, for example, we have 3 substeps of A, 3 substeps of B, and we run them concurrently. So that overlap between those 2 processes has some implications. First off, we might get many possible effective orderings of execution. In other words, what runs first? Well, it's either got to be A1 or B1, but what runs next? Well, if it was A1, then we could be A2 or B1. If it was B1, it could be A1 or B2, and so forth. So there are a whole lot of different orderings there. And because of that, when we run those 2 things concurrently, we don't know what ordering we're going to get. They could run where it's all of A and then all of B, or all of B and all of A, or part of A and some of B and then part of B again. And there's all kinds of ways. So that means the execution of those 2 processes being executed concurrently is no longer deterministic, because we could run it and get one ordering one time. We could run it again later, get a totally different ordering that's not even close to the first one. Now, here's where things get a little interesting for concurrency, that because the execution is no longer deterministic, some orderings might lead to a different result when we run the program. Or some versions or some orderings might result in problems where the program locks up or the program gives a bad answer that causes bad things to happen. And we're going to talk about classifying those kinds of errors later on. There's really 2 main classes of kinds of problems that we'll run into. But the main thing here to note is there are a whole lot of those orderings that could be possible. Some of them could lead to problems or bad results. And testing your program might not always reveal them, because when you run your test, you might only get good orderings. And with a relatively small program size, process size, with 2 processes running concurrently, the number of effective orderings could be more than the number of atoms in the universe. But there could be just a few sprinkled throughout there that cause really horrible things to happen. And that means that those errors or bugs are not going to necessarily always show up during testing. But if you have a possibility that you could get one of those errors, then it could come up and you could have a catastrophic result because of that. So that's why we study concurrency. All right, so circling back to that question or emphasizing a little more, why do we study concurrency? Well, there's a number of reasons. First off, modern CPUs have multiple cores in it. So your laptop or desktop gaming computer, whatever, probably has more than one core in it. Your cell phone processor for your smartphone might have more than one CPU core inside it. Those processors might also have SIMD support, which stands for Single Instruction Multiple Data, which allows you to load a bank of data in and have it all processed kind of in parallel, which those things allow us to write code that takes advantage of those multiple cores or those SIMD processing units to get faster execution for our programs. And that could be important for a game that have a really high frame rate or be able to have really beautiful visuals or a whole lot of physics simulation going on. It could be important for an industrial system or industrial machine, or it could be important for some embedded system to get fast execution by using more than one core, just like your smartphone does. Also, the GPUs, the graphics processors in your system, have this kind of massive SIMD processing capability or stream multiprocessing capability in them, or symmetric multiprocessing capability in them. And so those are also designed to have faster execution, better frame rate, more polygons processed per second, And so if you want to be able to take advantage of those, you need to understand something about concurrency and how to control it. Also, the operating system itself. I would bet right now your whatever device you're watching this on video on is running a whole bunch of processes at the same time. If you bring up something like your task manager and take a look at all the things that are running, there's just tons of stuff that's all running at the same time. They all have to share the same hardware, the same resources, the same memory. And so doing that in a way that is smart allows us to utilize those resources and share them in a way that is safe and less likely to cause problems. Also, systems that have to respond to some sort of events, like an event-driven programming system or an interrupt-based system. The computer doesn't know when you're going to press a key or move the mouse, but it still has to handle all that stuff when it does happen. But those events could come in any order, any result. And so you have to be careful about what you're interrupting with an interrupt or what you're handling one event based on other events that have already happened or might happen. It just takes some consideration, and that's a form of concurrency. Also, some systems are inherently concurrent, like you have, I don't know, like a communication system. We have a server and a client, and the client needs to talk to the server. You've got two programs that are running, just like A and B with their instructions, but we need to control the order of the sequence so they don't get out of sync or corrupt the data that's being transmitted or miss data in some way. So communicating systems, network systems, also any system that's sharing some kind of files that are on like a server drive, or sharing a resource or a database of some sort where some things are updating it and other things are reading the data out of it. Those are all things that require concurrency controls to be able to do without bugs. Now, like I said earlier, testing may not reveal problems like these, and pitfalls can be really catastrophic. So again, that's why we study concurrency. All right, and that's worth repeating. So concurrent programs can have concurrency bugs that could be hard to find and are not revealed by testing. It's not deterministic. As soon as you have concurrency, no longer is the execution deterministic. So you could test and test and test and run unit tests and make an automated tester that runs different scenarios over and over. You might never see that bug, but then you put this thing out in the field, bad things might start happening if you're not careful. All right, so also those bugs, when they do happen, because they could be a really rare ordering that doesn't come up very often, they could be hard to reproduce. And they could be, when those bugs manifest themselves, the results could be catastrophic or even deadly. It could kill people because of badly written software. And so one of the reasons we study concurrency is because it's best to avoid those problems, because you can't find them by testing the code all the time. So it's best to know what patterns result in problems and how to avoid those things in the systems you design. All right, so let's look at a couple examples here to finish up of concurrency bugs. So here are two to start with. The first one is the V-22 Osprey, which is a vertical takeoff aircraft like this. This is actually a really unique aircraft. So it works kind of like both a helicopter and it also works like a plane. So you notice this is in the vertical takeoff mode. It points its propellers up and it takes off like a helicopter. But once it's in the air, it transitions to flying forward and it flies like an airplane with propellers, like an airplane with propellers. So it's kind of goes between a two-rotor helicopter to an airplane with rotors on the front. And you'll notice that it's in the vertical takeoff mode now, but you can kind of see, and you can see right there the shape of that airfoil and see that that's rotated. So when this thing goes to flying forward, these two things will slowly rotate in the forward position. It'll gain momentum and then it will fly like an airplane. Now, the problem with these aircraft is it's a complicated transition between vertical takeoff like a helicopter and then flying it like a traditional airplane. So there's a computer system on board that kind of manages that system, and it's since it's so complicated to do that transition, they need to like push buttons and change things to make it take off and then transition it to flying forward. And the computer will take over and it'll handle that. Well, it turned out that in December of 2000, one of these killed 4 Marines because it crashed. And it crashed not because of pilot error and not really because of any kind of equipment failure. There was a minor hydraulic leak, but all that did was create an alert that showed up on the panel inside of the aircraft. And the soldier that was flying the aircraft saw the error, and he decided, well, maybe it's not a real error because everything seems to be going fine. And he hit this reset button. And part of the problem with hitting that reset button was that it basically, if you hit that reset button at just the wrong time, and you were in between transitioning from vertical takeoff to forward flight for air or helicopter mode to airplane mode, if you hit that at just the wrong time, then it could result in the rotors actually losing speed because they had to be at a higher speed to be in vertical takeoff mode than in airplane mode. So when you reset that system and it was in airplane mode, it says, oh, I'm in airplane mode, I'll lower the speed of the rotors, but they weren't all the way forward yet. They were in the middle of the transition, but hadn't fully made the transition. So what happened was he hit that reset button, the rotors slowed down to fly like an airplane because that's what the computer said it should do. And then it started to fall and lose altitude, and he hit the reset button again, but was already in that bugged mode. He hit it something like 8 times as they plummeted straight down 1,600 feet, and there was no way that the pilots could control any of that or take it over because it was the computer's job to do that when they were during transition, and it was kind of locked into that transition mode, and there was no way out of it because of a concurrency bug in their flight control software. So at least 4 people in this case were killed by a programmer not being careful enough with these things. Let's look at a couple other examples. The Northeast blackout of 2003. And in 2003, there was a concurrency bug in the monitoring system that monitored the power grid for the Northeast of the United States. It also went into Canada. And you'll notice here's a satellite picture of that when that blackout happened. All of this here, this is actually no power at all. And it was off for several days in some places. So all of this completely out. Normally this is all lit up. This is like New York City and Boston and all the way up into Canada up here and over there, all the way into actually northern Ohio and down here near Washington, D.C. All of this had no power at all. And here's why that happened. That they had a monitoring station set up where operators would watch and they could see the load on different generators and in different stations. Well, there was apparently there were some high winds, I believe in Pennsylvania. You can look this up specifically if you want to know, but I believe there were high winds in Pennsylvania that made some power lines droop and touch the tops of trees. Well, that created this excessive load condition. But what happened was the monitoring software that talked to those power station subsystems had a concurrency bug. And when it tried to read the value, it had outdated information that never got updated because of that concurrency bug. And so the operators were watching their displays and everything said, green, fine, everything's great. But it wasn't being updated. So the load from those lines eventually got so high that it brought down one of the power stations. The power station basically reached excessive current limit, and it shut down the whole operation rather than damaging something. Well, since nobody in the office was seeing anything change, that whole station went down, but the people that were operating it, which are actually in northern Ohio, in a kind of an operator control room, they never saw anything change on their displays because of the bug in the software. And so they thought everything was fine. And when that system went down, other systems tried to compensate by providing more power onto that part of the grid, but then they got overloaded and they went down. And so it was like a domino effect where substation after substation just went. Think of like circuit breakers tripping. Like, pow, that one in Pennsylvania goes off. All of the ones around it start going off. The other ones try to compensate. They go over their threshold. They all go off. And the kicker here was nobody could control it or monitor it because of that single concurrency bug in their software. So it was a cascading failure, and it ended up with over 55 million people without power in some cases for several days while they figured it out and figured out how to get it all back online. And the scary thing is that that system ran for a lot of years before that bug manifested itself and before that happened. And again, that's because of that. When you have a fairly complex piece of software with concurrency, there are a whole lot of orderings, and there might just be a very small number. It could even be just one that causes this problem to happen. And it might never come up, but when it does, it could be catastrophic, as we see here. All right, a couple more examples. All right, the ETEC3702. That was a radiation therapy machine used to treat various forms of cancer, primarily thyroid cancer, brain cancer, things like that, to shrink tumors. Now, the way radiation therapy works is you beam radiation at the tumor and you focus it so it affects the tumor more than all the rest of the body, and it kind of kills the cells of that tumor. It also has some side effects. That's why people lose their hair and things like that. But what happened was there's this company that designed this, the ETEC3702, in the 1980s, and they did all of their software in-house. They tested it all extensively. They ran tests. You put this input, it works right. Put this input, works right. And they had a whole testing regimen in place. Well, then they put it into practice, and there were bugs in the communication software between the operator terminal, where the operator put in the power level and the other information necessary to run the machine. And what they had done during their testing was they tested it kind of very slowly. You put in this number, you check the result. Yes, it worked. Put in this number, check the result. But what happened as operators got good at using the machine is they would put in stuff relatively quickly. Put in the power level, put in the other information, put in the angle, put in the position, hit go. The problem was that when you went through that software very quickly, there was a race condition that would happen. There are actually several bugs in this that were found later after they figured out that it killed people. But they were all concurrency-related bugs. And the idea was you'd put in one thing, it would be taking that one and adjusting things. And then when you put in the next setting, it totally missed that because it was busy processing the previous command when the next one came in. So there were cases where commands got ignored. And the end result was that the machine gave doses over 100 times the normal amount of radiation to certain patients. And that caused 3 known deaths and other numerous people that severely injured by radiation burns. One of the guys jumped up off the table when they turned it on and screamed and said that it was like the electric shock inside of his brain, and he went running from the room. And then a few days later, radiation burns appeared all over his head, and he was dead a few days after that. A horrible, horrible thing, all because programmers didn't understand how to deal properly with concurrency in their software. Healthcare.gov, this is a little bit different problem. And I don't know why I still have the blackout picture there, although I guess it makes sense. But healthcare.gov system in 2013, 250,000 people tried to enroll. And here I'm going to pause this for a second and change that picture out to something more appropriate. Okay, so we're back, and I changed that out to the actual error message that people saw when they tried to use the system. That they rolled that out. They said, hey, on this date, everybody can enroll for the government healthcare exchanges, which were part of the Affordable Care Act. And they rolled it out. Well, 250,000 people tried to enroll. On that first day that it was available, 6 people actually completed their enrollment. And that was a resource allocation problem where they had done testing on individual things, but not on a system under load with a lot of people accessing at one time. Again, concurrently accessing the system caused the system to crash and go into an unstable state and become completely unresponsive. So out of the 250,000 people that tried to use the site, only 6 were able to on that first day. It was a horrible experience that was all because of not thinking through how to deal with that number of users on that system that they created. Now, one other one that I'm going to talk about, there are other ones of these as well that you could find, but the Mars Pathfinder rover in 1997, it landed on Mars, was hailed as a great success. They kind of dropped this balloon thing on the ground, it bounced around, the little Pathfinder robot came out and started doing its system checks for the first few days, and they're like, wow, this is a fantastic success. A few days later, the whole thing locked up and they couldn't communicate with it. And then it rebooted itself. They're like, well, what happened? That wasn't good. And nobody knew why. And it turned out that in their system software they had for it, there were these non-deterministic sequences of events that would happen where it had to communicate and it would lock things out. And all of those things in that robot used this shared communication bus to talk between the different parts of the robot. Well, when something's using the bus, it needs to lock everything else out of doing that. Well, they had this situation where something could lock something out, and then another event could happen, which would then have to wait while the bus was locked out. But they had this case where it could lock out the bus, and then another event could happen. That thing would have realized it happened, and the bus was already locked, but it would enter a state while the bus was locked, waiting for it to be unlocked. And now you have this problem where the whole system locks up. And it all turned out it was some sort of bug in concurrency in the form of interrupt priorities for those things, where one thing had a higher priority, but it would still wait if the bus was taken by something with a lower priority. And so now you have what's called a deadlock state, where you have something waiting on a condition that will never happen, and another thing waiting on that to complete, which is never going to complete, and now the whole system locks up. And so the only recourse at that point is total system reset. And it turned out that back at NASA, they had a really difficult time replicating the error because it was all just based on timing of it. If the wrong sequence of events happen, whereas interrupts happen in just the wrong order, again, think about those orderings, but think about it rather than 3 things and 3 other things. Think about it as thousands or hundreds of thousands of things and hundreds of thousands of other things with hundreds of thousands of other things. There's a bad ordering that could happen that would cause it to lock up. They eventually were able to replicate it and figured it out, and then uploaded new firmware to it remotely, and it was successful at that point. But again, imagine that if they hadn't built in a watchdog timer system to reset it, they would have spent all this money sending it up there, and because of a single concurrency bug in the system, the whole thing locks up and becomes a brick at that point. All right, one final thing here. Concurrency bugs wise is every commercial project I've ever worked on. And I've been working as a professional programmer for a lot of years, programmer and engineer. But most of the hardware projects that I work on that involve making little embedded system kind of things, sensor systems, those all have interrupts in them. And they all also might have more than one process that's running to handle different parts of the code. And so you have to be careful with that, or you'll lock things up, or you'll get corrupted data. Anytime you have shared data in memory that can be touched by more than one process or an interrupt handle and other things, you got to be careful with it. Anytime you have 2 programs that are looking at the same file, like a web-based system or something that's running in the cloud. Anytime you have race conditions where one thing is modifying something, another thing is using that thing that's been modified, is a case where you have to be careful. Corrupted data from hardware components. I've had that happen. We're using a sensor like a gyroscope, and it's let's say it's a 16-bit output on the gyroscope, meaning it has 2 bytes. You have to read the first byte and then read the second byte. Read the first one, read the second one. Well, when you're reading those, what happens if the value changes after you read the first one, but before you've read the second one? You'll have half of one reading and half of the other reading. And now you'll have a value that doesn't make any sense. It's like corrupted because you've split that in half. So those kinds of things can happen. Database records in a database that are being accessed. Communication subsystems or communicating subsystems where they have to talk to each other. And you have 2 pieces of code in different places that have to communicate with each other, like a wireless system. So real world systems are rarely simplistic, single-threaded, standalone programs like you've written for a lot of your labs in your academic career. A lot of times it's multiple systems working together, like a cloud-based system or a embedded system or a network-based system, network game. And so as soon as you have concurrency, you open up yourself to non-determinism, which opens yourself to a whole host of problems that are difficult to spot during testing and may never show up in testing while you're testing it until you deploy it, and then you can have things go wrong. And when they go wrong, you can use radiation to burn people or make their aircraft crash or cause 55 million people to be without power, including businesses and other things that rely on that to make their money and keep people safe. So that's why we study concurrency. Every large project that you're going to run into, every commercial project is probably going to have some kind of concurrency of some sort in it. You need to know what the pitfalls are. You need to know how to spot them. You need to know how to plan to avoid problems with them. It's also a really cool thing because you hear people talk about, like, well, computers are completely deterministic. They just do what they do. You run a program, it does what it does. And I actually heard some of that nonsense when talking about the election results. Well, the only way the election machines could get something wrong or have an error that needed to be accounted for is if somebody hacked into it and changed it. Well, no, if you have tens of thousands of election machines all gathering the data and reporting them somewhere at the same time, that's a recipe for concurrency disasters if somebody wasn't careful about that. Fortunately, all of the election machine companies have third-party code reviewers that specialize in finding things like concurrency bugs that go through and try to find those. But the idea that a program can't just accidentally do something, or if you run it once and does something and you run it again, it should always do the same thing. As soon as you involve concurrency and have non-determinism, it's not the case. You could run it once and get one answer, run it again, get another answer, run it a third time, it locks up. Run it a fourth time, everything's fine. Run it 100 times or 1,000 times or 1 billion times in a row, everything's fine, and then one time locks up. And it's all not because there's something wrong with the hardware of the computer, it's just because those orderings, you're kind of playing, it's like having a gun with a single bullet in one chamber, the rest of them are fine, and spinning it and trying it over and over again. The problem is we have to know what those bugs look like and know the pitfalls and know how to avoid them to write good software that's reliable. Okay, that's all for today. The one thing I want you to do is complete that Lab 0, which doesn't really have anything to do with what we talked about, but that's a thing for you to make a little document to turn in so I can see your picture and have a name to associate with it. Also, it'll work out any bugs if you're having trouble putting things into Blackboard and uploading them. Hopefully Blackboard does not have any concurrency bugs. I believe some parts of the MySSU system might have concurrency bugs because I put in clearance for registration and had it not really clear it, even though it told me it did. So, but complete that Lab 0, turn that in, and next class we're going to dig into concurrency a little bit further and start looking at things, and then we're going to quickly get into we're at the point where we have some labs in the class. All right, that's it for today. Everybody stay safe, wear a mask, wash your hands, and I'll see you next time.